Okay. So hello, everyone. Welcome to another VTSS seminar. Today's guests are Kenwin Maung as speaker and Ed Herbst as guest panelist. Kenwin, the floor is yours.
All right. Thank you so much for having me over. So today I'll be talking about basically local projections. Um, Everyone is talking about local projections. I think it has become a very popular alternative to estimating impulse responses, uh, as compared to using DAR type of. I mean, people still use it, but I would say that local projections have surged in popularity. Today I'll be talking about estimating impulse responses that could be varying over time. So I'm going to first present you the basic vanilla plain old local projection. And over here, we're going to assume that we have an observed shock for simplicity. Basically, local projections is going to be a direct forecasting approach. You're going to regress the variable that you want to, whose response that you're interested in looking at. Let's call this YT plus H, for example. It could be inflation in the future, H horizons in the future. Regress it on a shock variable of interest. And you can also include some of the controls, which are going to be exemplified by the XD over here. The controls typically would include like lag terms of the variable itself, and it could also include the lag terms of other endogenous macroeconomic variables in your system. We also include an intercept here. And I believe that a large part of this, popularity of local projections is that it's really very simple to compute, both in terms of estimation and inference. I'll come back to the point on inference later on, but in terms of estimation, at the end of the day, it's really just OLS. You conduct an OLS regression for each horizon of interest. And is more recently, there has been some work that show that local projections are relatively more robust to misspecification in estimating the impulse responses and also conducting inference, getting the correct coverage probabilities for the impulse responses when compared to that of a VAR. So this is shown in the Monte-Olea paper. They suggest they construct an underlying DGP to be that of, say, a VAR with a moving average component, moving average infinity component. But the MA component is going to be, the misspecification is in the MA component because when you estimate the VAR, you tend to ignore the MA component. And the MA component is going to be the misspecification, and the misspecification is going to be, somewhat of a local to zero type of thing. So there's some small amount of misspecification. And they show if you were to use local projection, well, projection can be robust to that type of specification in that the distribution of the impulse responses are still going to be relatively unbiased, while that of the VR would be biased. Now, intuitively speaking, basically at the end of the day, if you ignore the MA component, you have some sort of omitted variable bias. You're going to estimate the VR coefficients incorrectly. Your variance covariance matrix is also likely going to be subject to that omitted variable bias. As a result, if you look at the impulse responses, which are going to be, the impulse response in a VR are going to be generated iteratively. They're going to depend on the coefficient matrices of all of the lags. If they're misspecified, if they're estimated with error, then that error is going to be carried forward for each horizon of your impulse responses. So that's the gist of, the paper. So it is a specific DGP that they have, the underlying DGP, but it is relatively general too. Okay. So the main point is local projections a bit more robust than that. Although there are some trade-offs between local projections and VARs in terms of the bias and variance. Okay, so that's that. That's the basic vanilla local projection. But if you look at very popular macroeconometric papers, they don't tend to use that vanilla approach. They tend to try to include some sort of instability, and this type of instability is often due to time varying instability. So in this paper on monetary policy, they show that the impact of monetary policy on macroeconomic variables varies if you were to look at whether or not you're in an expansion or recession. And they actually did find that monetary policy is less effective during recessions, which is, I believe, a sort of like counter to what people have been finding before this paper, that they found that, monetary policy tends to be very more effective during recessions. Over here, the type of local projection that they're using is known as a smooth transition local projection, which I'll be coming back to in a couple of slides. There are also other papers to study government spending multipliers. So these multipliers are going to be a function of some impulse responses. And they note that, you can have different spending multipliers depending on which regime or which state of the economy you're looking at. So if you were to define the economy to be, or rather the states to be high unemployment rates and low unemployment rates, you might get one set of impulse responses. And if you were to redefine it to be, say, if the economy was to be restricted by the zero lower bound or not restricted by the zero lower bound, then your impulse responses might differ. And in fact, they did find the latter paper, the Randy and Zubair paper, did find that if you were to look at the government spending multipliers and compare it between high and low unemployment states, then there is not that much of a significant difference. However, if you were to redefine the regimes to be restricted and unrestricted by the zero lower bound, then you do get, notable differences, notable and significant differences there, right? When you look at the impulse responses. I think obviously there's some key limitations to such an approach because at the end of the day, before you do the analysis, you do need to define what you think these regimes are going to be. First off, you need to choose which variable, which state variable you want to use. You want to use unemployment, you want to use whether or not it's bounded by the zero lower bound. And then you have to, in the case of the unemployment, you have to pick how do I segregate, how do I, dichotomize it to be high unemployment and low unemployment. And the case of the previous paper, they chose unemployment above 6.5% to be that so-called the high unemployment state. And, if it's lower than that, it's low unemployment state. They did some sensitivity analysis by changing this number, but, that's not going to be guaranteed. And also, it really does depend on how you define the state or the regime variable. If you define it differently, then it's very likely that you could have it. Because it affects the timing of the switches, it could really result in very different estimated impulse responses. And the key question here is then how do we then reconcile all of these different results if you have all these different impulse responses? And then it's due to the fact that you have these ex ante predefined, the user pre-specified type of states. So the approach in this paper is going to be very different from this approach in that we're going to be taking an agnostic and data-driven approach. So first off, we're going to allow the impulse response functions, which are the coefficients in the local projection regression. They're going to depend on time. They're going to vary with time, but we're not going to say how it varies with time. So in the case of this smooth transition local projection over here, you do still have to specify how that smooth transition function looks like, and use like a logistic function. Over here, we're not gonna fix that function beforehand. We're not gonna say it's gonna be like a jump function. It's not gonna be a smooth function. We don't need the exact formula for the function basically. We want them to be completely non-parametric. There is some restriction that we require. Basically, we need some smoothness with the restrictions. That basically just means that the impulse responses cannot change too much over time. Okay, and we're going to estimate the non-parametric functions using a kernel approach, and over here we're going to use local mean. Okay. So there are some attempts at allowing for time variation and the coefficients of local projections. In this working paper, they adopt a Bayesian approach to estimate the time varying impulse response coefficients. But usually, if you use a Bayesian approach, you tend to have to specify some sort of the transition of the variable, the coefficient, and in this case, the typical specification is going to be that of the random walk. So it's still relatively parametric. There is an alternative approach by Atsushi Inoue and Barbarossa Irua, where they use the approach of this Mueller and Patelis paper. The specifics of this approach is quite complicated, but basically the assumption on the coefficient, the time varying coefficient is you can basically see it as, say, let's call the time varying coefficient theta t. Theta t is going to be equals to theta, which is constant over time, plus something that is time varying, maybe let's call it ct, but then that time varying part is going to go towards zero as the sample size increases. So you can see this as some sort of local to zero time variation. So in other words, their approach over here would be really well suited for, if you have time variations, but it is on a relatively moderate variation. In our case, we don't really need to take a stand of how much their variation is. However, we do have some smoothness assumptions, So that kind of does rule out the type of a jump type of variation. So there is a very related model, which is I see this paper, this JDES paper by GD Kao, as the VR counterpart of what I'm doing, basically. They used non-parametric kernel approach, local linear estimation to estimate a time varying VAR. So in their model, in the VAR, the coefficient matrix is time varying and is a non-parametric function of time. The variance covariance matrix is also a non-parametric function of time. And they use this basically the same kernel approach. And because they are estimating a VAR, they can also recover the impulse responses. I believe they have a reduced form of impulse responses, but the impulse responses are basically just iterations of the estimated coefficient matrices and also the error variance covariance matrix. The main difference between their approach and my approach is, of course, it's going to be related to the whole debate between VAR versus local projection. The first point, robustness in the specification, was what I pointed out earlier, and also computational simplicity. There is an additional point of difference that I would like to highlight. So going back to computational, before I go there, this computational simplicity definitely is related to estimation. In VR, you do equation by equation estimation, and then in order to get the impulse responses, you still have to do some sort of transformation. The local projection is directly obtained from your coefficient estimate. That is related to estimation. But it also extends to inference. If you want to construct confidence intervals for impulse responses from a VAR, so VAR implied impulse responses, then typically you rely on the delta method or some sort of bootstrap. The delta method is a little bit more iffy in the sense that first off, if you look at say Killian's textbook, you can see the asymptotic distribution for the impulse responses that obtained via the delta method, and it is very unwieldy. It is a big object, and it also really does depend on whether or not the underlying DGP is finite dimensional or a finite number of lags VAR or infinite dimensional VAR. You would have two different distributions. And that's probably why a bootstrap is a good alternative to that as opposed to using a delta method. For the local projection, your impulse response is the coefficient beta that is in front of the epsilon t over there. It is obtained from an OLS estimation. So you can easily construct confidence intervals with this beta using the regular confidence intervals for OLS. Of course, there is an additional layout complication over here for the local projection because the error terms or the residues are usually are going to be serially correlated, and then you have to think of some sort of hack adjustment for your confidence. But I would like to further stress, because this paper is basically a two-parter. In the first part, I talk about trying to estimate low-dimensional local projections, with time variation in a relatively finite dimensional setting, but you cannot always imagine the situation where you suddenly add too many controls and all of a sudden you have too many variables on the right-hand side of the regression. So that's what I would call the high-dimensional setting. And conducting inference in a high-dimensional setting is not straightforward. And we know that's not straightforward. And I would like to talk about how focusing the local projection framework can help to alleviate some of these issues. So if you want to do construct confidence intervals for impulse responses in a VAR, to apply dimensionality, first of estimation is no longer going to be straightforward. The simplest approach to estimating this high-dimensional VAR would be to assume, say, a framework of sparsity. So basically, only some of the coefficients in a coefficient matrix are truly non-zero. Everything else is zero. Or you can assume that it's approximately sparse, so that the coefficient matrix can be approximated by a sparse coefficient matrix. And then you select the non-zero coefficients using lasso, or an extension of lasso, adaptive lasso, the stat penalty. If you do that, however, first off, we need to note that, as I mentioned before, the impulse responses that you estimate from a VR are going to be that kind of nonlinear transformation of the coefficient matrix and also the variance covariance matrix. So again, over there, you might have to assume some sort of sparsity for the variance covariance matrix. So because it is a nonlinear transformation of all of these estimates, and if you use some sort of sparsity inducing technique, we know that in the event of a model selection error, which is likely going to be the norm rather than the exception if you were to use the lasso, in the event that you are selecting the wrong model, you have omitted variable bias, your estimates are all going to be, not reliable. The end result of that is that even inference for the individual coefficients themselves might not have, it might not be well approximated by a normal distribution, let alone a nonlinear transformation of all of these coefficients. Say if you were to conduct inference via the delta method or bootstrap, it is not guaranteed that the final object, this final transformation, is also going to be approximated by a normal distribution. So these model selection, variable selection errors can be compounded furthermore when you talk about these impulse responses. And if you were to assume the normal approximation to construct confidence intervals, then that might be slightly misleading. There are, work on sparsity inducing techniques in VAR is not it's has been explored. I wouldn't say more recently, but it's been explored since like 2015. But you can consider extending the post double selection procedure of Chernozyukov, Bologna et al. To vector autoregressions to get valid inference for a subset of the estimated coefficients. So in this paper, Heck et al., they did so in the context of Granger causality testing in a VAR setting. But this does have the restriction that we are only basically looking at a subset of estimated coefficients. We care only about inference about a subset of estimated coefficients, and the other parameters are, going to be regarded as nuisance parameters. Unfortunately, if we were to take this approach to estimate the VAR, again, the impulse responses are going to be a function of almost all of the parameters in your system. So, it's really hard for us to extend such an approach to that. However, if you recall, I said that in the local projection framework, the impulse response is if you have only one shock, the impulse response is going to be one coefficient. It is the beta that is in front of the shock variable. So the rest of the parameters, we get high dimensionality because oftentimes we want to include a lot of likes, we want to include a lot of other variables and the likes of the other variables. All those parameters, which we often include for efficiency reasons or because of the structural identification, we need to include that. These are mostly going to be nuisance parameters. The parameter of interest is going to be our impulse response. So this is exactly the same framework as the post double selection lasso framework, because again, we're only going to focus on one coefficient or a finite subset of coefficients, as opposed to we don't really care so much about the other control variables. So this is exactly that framework that we can get by considering a local projection instead of using a VAR. The VAR one would require a lot more slightly more complicated. You have to think about alternative approaches to deal with that. Having said that, I do have to point out that when it comes to high dimensional local projections, there are a couple of papers that have tried to deal with this. The first paper over here, so the post double selection lasso approach can be seen as an alternative to the specified lasso approach. That one of the key reasons why the lasso is not going to give us the typical normal distribution that we're interested in is because that this bias that is introduced by the lambda over there, by the penalty term. So the despecification or the debiasing approach over here can also be applied to the high dimensional local projection. I do want to mention that their approach do require you to construct this some sort of a approximate inverse of the gram matrix. So if you treat the capital X as your data matrix and capital X transpose capital X is the gram matrix, this matrix is going to be singular because in the high dimensional case, because you have more variables than observations, the rank of that is not going to be full. So there is no inverse for that. The inverse doesn't exist. You can have to construct an approximate inverse, and they use node-wise regressions to do that. So it's a bit more complicated. And I am not sure how to, I think that it is even more complicated when you consider that we're going to do some sort of a kernel nonparametric regression over here. There is also a separate, another approach by Juyong Cha, which is basically the post-double selection procedure, but instead of lasso, they use this so-called orthogonal greedy algorithm combined with high-dimensional AIC. The high-dimensional AIC over here basically determines how many variables you want to include in the final model. And then this orthogonal greedy algorithm is going to pick your variables, the so-called relevant variables, based on its marginal correlation with the target variable. So this is also another alternative approach. And another appeal of this approach is that it really doesn't require us to have any form of either exact sparsity or approximate sparsity. They have I believe they have a restriction over here where the coefficients have to decay, which is slightly similar to approximate sparsity, but a bit more general. We're going to stick with the less so. We want a completely linear approach. We want the less so because we're going to introduce some sort of non-parametric estimation. So I conjecture it's possible to extend it to all these, I guess, fancier approaches to get uniformly valid inference, but I'm going to stick with the less so for now, okay? And sticking with the less so also preserves simplicity because as I will convince you in a couple of slides, the procedure that I'm going to be presenting today can be done with package. You can use the R package for the less so. You can use, because at the end of the day, it's just OLS, weighted least squares. You can use the R package for the less so. So we're preserving parsimony and also computational simplicity, which is one of the key reasons, I believe is one of the major reasons for why people are very interested in local projections by sticking with the less so. Okay, so at the end of the day, the model that is in my paper in our project is exactly the same as the vanilla model that I showed you above. We have an observed shock. However, you have to note now that all of our coefficients are going to be sub-indexed by little t. So little t is the time index. And I didn't write it here, but the residues, or rather the error terms over here, has a variance. And the variance can also be, and the variance typically will be sub-indexed by little t. So we allow the variance of the errors to vary over time. And if I were to collect all of the interceptor and without loss of generality, I'm only going to consider one shock, and I'm going to put it in the first position. So if we collect all of the regresses of our regression, I'm going to call this capital XT, then our coefficient vector is going to be this gamma t over here. Gamma t does depend on the horizon we're looking at because it's the local projection is local to the horizon. So we're going to estimate this we're going to re-estimate this equation for each horizon. The key assumption here is we're going to assume that the coefficient vector is a function of time. It is a non-parametric function of time, but it's going to be a function of standardized time. So that means the support of this function gamma is going to be from 0 to 1. And the reason why we have to do this standardization or normalization is for consistency reasons. And basically the idea is that you hope to have, as capital T increase, you hope to have as more and more information in a local region at time point t, local to time point t, and that helps guarantee a consistency of this gamma at that time point t. The key assumption is that we're going to assume that it has continuous second order derivatives. So this rules out if you were to have a jump or a structural break, a discrete structural break at time t. So for example, you have a regime switch at time t. The results of the paper would not be able to consistently estimate gamma h at that time point, at the break. So, but away from the break, we can recover consistent estimation of the impulse responses. I mean, basically it's saying that if there are finitely many discrete structural breaks, then those points are not going to be estimated properly or well enough, but you can have the guarantee for the rest of and after the break, assuming it's still smoothly varying, you are going to be able to recover those type of responses. So this model that I presented over here, this is our baseline model. It is relatively reduced form. I just said that we have this epsilon t is a shock variable. The epsilon t basically is going to be a placeholder. So you can see this as either a reduced form local projection, or it could be a structural local projection. Epsilon t is just a placeholder for the user's pre-specified structural identification. So if you want to use an observed shock, so epsilon t could be like, in our paper, we're going to use an observed weather shock. You can use like a fiscal policy shock, a constructed fiscal policy shock, oil shocks, oil supply shocks of Killian. Or you can also, if you look at a paper by Monteolia and Plugman-Moller, which talks about the equivalence between local projections and VAR impulse responses, they talk about how to replicate a impulse response in a VAR setting in a local projection setting. So structural impulse responses in a local projection setting. So for example, if you use recursive identification, in the example they gave was if you have a typical monetary policy VAR where you have an interest rate variable that is ordered in the middle, and above it, above the interest rate variable, you have the real economic variables, you have price inflation variables, and after the interest rate variable, you have things like financial market variables, things that react contemporaneously to a shock in the interest rate, or monetary policy shock. Then what you would do is that you would have the interest rate, the policy shock, get exemplified by epsilon t. And in your controls, you not only have to include the lag terms of all of the variables of the system, you have to also include the contemporaneous variables related to the variables that are ordered before the policy rate variable. Okay, so this current specification is flexible enough to accommodate that type of structural identification that you commonly see in a SVAR. So so that's the reduced form framework. However, you can relate this to existing structural VARs. In this case, this is the this AJ macro paper. They studied the impact of weather shocks in the macroeconomy. So you can imagine a typical set of macroeconomic variables, some measure of real productivity, some measure of prices. And they have this constructed weather shock variable. They use a time varying VAR, and they have two sets. They basically have two sets of coefficients for two regimes. So you have a coefficient matrix A, it's going to be relevant to regime 1, and then matrix A I2 for regime 2. They also have two different variance covariance matrices. Their VAR is going to be a convex combination of these two regimes, and the weights for these regimes are going to be determined by time. So this is, again, standardized time. Basically, if you were at the start of the time sample, then this little t is going to be 1 over capital T. So this is very close to 0. So if you're at the start of the time sample, then the VAR is basically determined, the dynamics of the VAR is basically determined by this regime. As times carries on and moves forward, then the second regime starts coming into play and the first regime eventually drops out. So this can be seen as a parametric version of what we're suggesting, because this 1 minus t, this convex combination of this t over capital T is basically this guy over here, this non-parametric measure. It is a special case of this gamma being, 1 minus t over capital T and t over capital T. Okay, so this is we'll come back to this later in our empirical application, but we can see this as a sort of a parametric version of what we're trying to do. And you can also derive the impulse responses implied by this VAR, and then relate it back to what we're doing in this beta T over here. As I've mentioned, this JBS paper by G.D. Kao and co-authors, this is the non-parametric time-varying VAR. The coefficient matrix is going to basically unspecified function, and the variance covariance matrix is unspecified. Basically, you still do need both of these objects to have, smooth variation. You can't tolerate jumps. So over here, if you assume that the process is sufficiently well behaved, it is stationary, but in a local window, it looks stationary. If you look at it from a global perspective, it might not be stationary. But as long as we have stationarity in a local window, then it can emit a time varying vector moving average infinity specification. And we know that from the VMA infinity approach, you can get the impulse responses implied for either a reduced form approach or a structural specification. So then again, we can relate the impulse responses from this model back to this beta T. Now, something that's a little bit more different. So going back to that monetary policy application that I've mentioned, they have this weighted combination. So it's kind of similar to the T of a capital T, but over here, there's this logistic function. So you have, again, two different sets of coefficients for one local projection and another local projection. This is the coefficients from local projection in a boom, and this is a set of coefficients from local projection in a recession. And they're going to be a convex combination, and it depends on this. The weights of this combination is going to depend on this smooth logistic function that depends on a state variable ZT. So I believe the baseline choice that they use for ZT, little ZT, is that they're going to use the past 7 quarters moving average of GDP growth. So yeah, and this capital F over here is a logistic function, so it's completely parametric, and you have to estimate the parameters that you have to estimate not only are the betas, gammas, but also the thetas over here and the sigmas over here. It's a bit more complicated, but our baseline model right now is going to be different from this because first off, the first difference clearly is that we don't have this logistic function for this capital F over here. The second difference is we don't have this state variable zt. Our so-called state variable is completely deterministic. It's just a function of time. So I mean, if you buy the argument that we can't, it's a bit difficult for us to really determine what the state variables are, depending on how you define the state variables, you might get different results. Then maybe the agnostic approach that we propose could be some sort of robustness check for whatever state variable that you have in mind. So it could be a robustness or an alternative to that type of predefined user, supervised approach over there. Another point I would like to mention is that more recently in the paper by Elena Pesavento, Silvia Gonçalves, and co-authors, Lutzkilin and co-authors, they say that if you have such a local projection that depends on state, observed state variables, or rather constructed state variables, and your state variables are some sort of variable that could be affected by your shock, then these state variables are endogenous, then whatever impulse responses that you identify might not be it might not actually get the right, it might not actually be the one that you're interested in identifying. Okay, so over there, they have different definitions of impulse responses. And at the end of the day, the only impulse responses I believe that you can safely identify are impulse responses that are related to very small changes in your shock. And then that's fine. But if you were trying to do a large shock and you want to see the impulse responses due to a large shock, your impulse response estimates might be heavily biased. So there is also that additional layer of complication over there. But that is not going to affect us, at least for our baseline model, because we have a deterministic so-called running variable. It's just t. Okay. All right. So I do want to further point out that there is an additional complication due to the fact that we have to take into consideration the time series dependence, not just in our regressives, but also our error terms. The LP, local projection residues, are generally going to be serially correlated, especially if the underlying DGP is say a structural VER that is invertible and well specified. Then in general, the local projection residues is going to be a linear combination of the structural errors from time t+1 all the way to t+h. So that is going to be a serially correlated object. And your covariates are also, the control variables are also going to typically contain lag variables of the other variables in your system. We know that these things follow some sort of AR processes, and we want to avoid using, recently there's this push against, assuming these type of strong mixing or beta mixing type of characterizations of AR processes. There are some well-known examples where simple AR processes might not even satisfy strong mixing characterizations. So what I'm doing in this paper is that we're going to assume a very flexible class of weak dependence, which is known as tau mixing. So instead of strong mixing, which is alpha mixing or beta mixing, strong mixing implies tau mixing, but not conversely. Tau mixing is much weaker than that of strong mixing. It's a relatively flexible class of weak dependence. The type of processes that do not satisfy strong mixing, the classical examples of that are going to be satisfied in tau mixing. And it's also flexible enough for empirical process theory. Basically, for tau mixing, if you know about beta mixing, there's a coupling theory for beta mixing. Tau mixing also also enjoys that kind of empirical process theory. So that's what we'll be using as our measure of dependence. And also we want to say, just to emphasize over here, in many papers, the shock variable is often assumed to be IID. We're just saying that no, it might not be IID. You could have some sort of zero dependence, because if you think about the structural identification that I mentioned earlier with regards to the recursive identification, epsilon t, say if the shock was in the rate, policy rate variable, then epsilon t is the policy rate variable. The policy rate variable is an endogenous variable in the VER. By construction, it should have some sort of temporal dynamics, some sort of zero correlation. So there is no way that the shock variable over there would be an IID variable. So that is why we want this to be, have some sort of flexible dependence over there too. Okay. So the key assumptions that we have is we're gonna, you need to have at least 4 moments of all of our controls. The error term the residues could have as low as 2 moments. So potential, some sort of heavy tail could be accommodated. And we're not gonna impose any sub-Gaussian assumption. Well, if you impose sub-Gaussian assumption, then all of uh, the moments exist. And we're not gonna do that. And this is typically the common assumption that you make for high-dimensional Lasso type of analysis, at least subgussion is subwayable. And for the moments, so basically we potentially allow for heavy tail shock. The moments over here, as you can see, the moments of the controls, no, all the variables, the moments of the error term, they can also depend on time. So the moments depend on time, then clearly we don't have stationarity. But this type of non-stationarity is not so bad because we're basically just saying that the moments are varying, but very smoothly. So if you look at it at a local window, then the type of variation is not so much. It basically approximates a stationary series if you look at it from a local point of view. Okay. And also the covariance can also be varying over time. So, I mean, there's a lot of discussion on whether or not typical macroeconomic variables like inflation, are they stationary, is unemployment stationary? Well, you don't really have to, at the very least, because we accommodate that type of it's more flexible. It could potentially accommodate these type of variables without really having to take a hard stand on saying that, okay, these variables are definitely strictly stationary. Well, might not necessarily be the case. Okay, let me talk about the local linear estimation from an intuitive perspective. So over here, we have the original model. And over here, I'm going to index everything by little s. Think of little s as some sort of time point that is different from little t. Little t is the time point of interest. We want to estimate the impulse responses at little t. So we are looking at other time points, little s, that are around little t, but not exactly little t. Because of our assumption that this is two continuous uh, is sufficiently smooth, has two continuous derivatives. Let's do some sort of Taylor expansion over it, and we evaluated a little t. We have evaluated the time point that we want. So you can see that this is the main object that we're trying to estimate, but it's multiplied by some variable, multiplied by the variable regresses, but at another time point. And we also have, by virtue of the fact that we're using this local linear expansion, we also have the first order derivative appearing of the gamma over here. This is not the object of interest, and of course the difference between the arguments. This is not the object of interest. This is the object of our interest. So even though we're going to estimate both objects, the level terms over here and the derivative terms over here, we are oftentimes going to discard the derivative terms and just keep this. We're just going to keep in mind this over here. Okay, so because of this little s, now we have to think, okay, what kind of little s do we do? We are going to basically look at the time points that are around little t. So we're going to use information that is close to little t, and hopefully they have something to say about the impulse responses or the coefficients at little t. If we look at the coefficients around, if we look at the data around little t. So if you think of this really simply, if you think of a simplest explanation of this, you're basically, in order to estimate time varying coefficients, the simplest version of that is basically just a rolling window. You're going to take data around that time point, use that data, and then estimate, say, the time point of interest in the midpoint, use the data around that time point and estimate that the coefficient vector for that time point. And it turns out that actually the rolling window is a specific case of the type of estimation, the kernel estimation that we're doing today. We're doing instead of giving equal weights to every single time point around little t, we're going to give kernel weights. So if you think about like some sort of kernel that gives more weight to the time point that is closest to little t and less weight as you move out from little t. If you look at data further away from little t, you give a declining weights to that. That is like a weighted way of doing a rolling window. Rolling window gives uniform weights to all of the time points around t. And basically, if you exclude this first derivative term, and if you were to use a uniform kernel, then it directly coincides with the rolling window estimation. But in this case, we have this local linear estimation, so we're estimating also the first order derivative. Now, the reason why we're doing that is theoretical. It's because that if you include the local linear term, the derivative term, then the bias of our estimator at a boundary is going to be of a smaller order. So the bias is is not as big. If you were to exclude this, then the bias at the boundary could be significantly larger. So this kernel is basically given by this. The capital K is the kernel function. It's going to be dependent on the how far you are from little t if you're looking at a time point s. And this is going to depend how much information we're going to basically include our kernel in our window is going to depend on this bandwidth. So the B, you can think of this like a rolling window width. This B over here is the kernel bandwidth. Ideally, we want the kernel bandwidth to go to 0 as capital T goes to infinity. Capital K is going to be a symmetric PDF. The type of you can consider things like a Gaussian kernel, or well, Gaussian kernels are a bit more complicated, but the type of kernels we're going to use basically have the idea that we're going to give more weights to time points around T and then less weight outside of T. Okay, so the key point that I want to emphasize with this is this kernel function is going to assign positive weight. This kernel function is always going to be at least greater than or equals to 0. That's a square over here. If this is positive, at least not negative all the time, you can take the square root of this guy. If you take the square root of this guy and then you square on the outside, you can bring it into this regression over here. So I do have to mention that this is just a regression of your target variable on all of the regressors, and the regressors multiplied by time difference. This S minus T divided by capital T. S, T, T is your specified time point of interest. S is other time points. You see, we're looking at from the first time point all the way to capital T minus H. This is the last time point that we have. All of these objects are deterministic. These are known objects. So you're basically, if you were to look at it from an Excel spreadsheet point of view, you're basically taking the regressors, multiplying all of them by this object over here. So this is just a linear regression on something that you know and on something that you know. And then if you bring this, the square root of this kernel thing, the kernel function is specified by you. You know what the kernel function is. And then you can compute this. At the end of the day, it's just going to be a number. You can bring this into this function, the square function, and you end up with just transformations of the dependent variable, transformations of the independent variables. You can do a regular OLS regression. So this is super fast. It's just OLS. Once you transform all of your variables, this is just OLS. And if you were to compare this with, say, a Bayesian approach, so I know that for the Bayesian time varying, this paper to run one round of Bayesian, and so they use Bayesian approaches to estimate this model. To do one round of estimation takes 2 days. This OLS estimation takes less than 5 seconds, less than a couple of seconds. Doing time varying estimation using this sort of like weighted rolling window could potentially have computational advantages over those type of Bayesian fluid space methods. Okay, so I mean, at the end of the day, there are going to be some advantages to the Bayesian approach that I'll talk about later in the empirical application, but I would like to emphasize that this is super simple. So even though we have generalized it to this, non-parametric time varying approach, we are still preserving that parsimony and computational simplicity that people love about the local projections. Okay, so I have some theory over here. Basically, I am saying that your estimate, so the last part is more important, the estimate of your impulse response, or rather the vector in the local projection regression, vector of coefficients of local projection regression is going to be normally distributed. It's going to depend on, so this omega h over here is going to be the long run variance, because we have assumed that we basically allow zero correlation everywhere. So this is going to be a measure of the long run variance, and then it's going to be pre and post multiplied by M. Capital M, if you recall, is just the expectation of the X transpose X. It's just X and X. Okay, so this is the typical sandwich formula. We do have this little nu zero over here. Nu zero is a parameter that's related to the kernel of choice. So for example, if you were to use the typical kernel, which is the E kernel, I can't really pronounce it, but is the efficient kernel, then nu zero is basically going to be, I believe, the 2/5. So it's just a number. You just need to multiply the number, a scalar number, to this object that you can construct sample versions of these objects. So I do want to point out that this long run variance thing, the typical approach to estimate, that is to use I think the most popular approach is to use a new mass estimator. In the non-parametric setting, it turns out that there is a very natural estimator thanks to the fact that we're using the non-parametric estimation. Part of the result, part of the proof of the consistency of the normality result over there is you have to show that the expectation of the score vector, so basically the regressor multiplied by the error term, weighted by the kernel. This object, if you take the square, the transpose of this object, this guy, the expectation of this guy will converge, the limit of this expectation will converge into the long run variance multiplied by this new zero. So in other words, in order to get the long run variance, we can just construct a method of moments, a sample version of this thing. Just replace the expectation by the sample average. So the sample average version is this guy over here. However, we don't observe the local projection residues, but we can use a construction of the residues from your local projection, plug it in there, and then this is going to be your sample estimate of the long run variance. This is not the new West estimator, even though we're using kernels over here. This is not the same kernels in the new West estimator. This is the kernels in the time domain. The kernels that they're using is in a frequency domain, but it's a very similar idea of here. So you can easily construct from your estimation as a byproduct of your estimation the long run variance estimator. And I do have a result that, along with additional long run conditions, you can show that this is going to be a consistent estimator of your long run variance evaluated at time tau. So time tau is just, T over T. So what I'm talking about, so this omega hat over here is this guy, which is the method, it's just a sample version of this expectation. And then for the M's is the expectation of the X transpose. You can easily show that all you need to do is construct the sample version of the X and X transpose, weight it with the kernel, and then that will be a consistent estimator for the expectation. So then this would be your sample construction of this guy over here. Now, if your shock is in the first position, then your standard errors is going to be, this is going to be a matrix, and your standard errors is going to be the first element of that matrix in the diagonal over there. So there's the 1-1 position. So not only is it simple to construct time varying impulse responses, estimate the time varying impulse responses, it's just OLS. Your long run variance estimate can be obtained immediately as a byproduct of what you're doing. You're getting the residues anyway, you can immediately construct this. This is not difficult to estimate. So you don't have to resort to Nui West to do that, okay? Now, I want to talk about something a bit more exciting. I have not a lot of time left. I thought I was only going to take 40 minutes, but this is going up to an hour. Okay, so interestingly, at the start of the presentation, I said, okay, there are a lot of benefits to looking at local projection, especially if you have a high dimensional setting, because all of these other control variables, they're nuisance parameters. You want to keep the impulse response coefficient. That's all you care about. Now, it's quite easy to get a large number of control variables in our setting, in the non-parametric setting, because recall that when you do the Taylor expansion, now you have to estimate also the first order derivative. So you have so basically you have two sets of 2 times the number of control variables, 2 times the number of regressors. And at the end of the day, if you look at the kernels is giving non-zero weights to time points that are around t, but then if they're far enough, they don't give any weights. It gives a weight of 0. So effectively, your effective sample size is very small, much smaller than capital T. Okay, so you have a smaller effective sample size, and you have 2 times the number of regressors. So this might result in a large P, small N problem. So we're going to try to use Lasso to help us, and to recover valid inference, we're going to use pulse-level Lasso. Typically, Lasso is not going to be variable selection consistent. It's not going to be model selection consistent because you have to make some really strong assumptions. Basically, the irrelevant variables and relevant variables have to be the simplest way to the strongest sufficient condition for that is that they have to be orthogonal to one another. They cannot be correlated. But that is really hard to guarantee, especially in this case where almost every single variable, if the true underlying DGP is a VAR, then every single variable is endogenous. There's some sort of a dynamic dependency over there. And you would have omit the variable bias, the inference is not going to be normal. So we're going to use the post-double selection procedure. So over here, I'm going to have to define a system of equations. We're going to have the original local projection, which is given by this object over here. Now ZT, again, I'm only going to consider one shock over here. ZT is basically all the other regressors. So you have the intercept, and you also have the other variables, the other control variables. And I'm also going to define a reduced form relationship between the shock of interest. So this is basically to control the omitted variable bias due to correlation between the shock of interest that you want to keep and ZT, which you could potentially omit. So the reduced form regression relates epsilon t to ZT. And if you do a substitution, substitute epsilon t into epsilon t over here, you can re-express y, oh, there should be t, yt plus h as a function of just ZT, just by substituting this over here. So we have two equations over here. We relate epsilon t to ZT and the target variable y with ZT. Now we're going to assume that only some of the coefficients in this parameter vector, this theta, and some of the coefficients in this parameter vector, they're going to be non-zero. Everything else is going to be zero. So we are assuming exact sparsity. It is possible to extend this to approximate sparsity. It's just an additional, more algebra, basically. But at the end of the day, as long as the approximation error is small enough, smaller than the estimation, the rate of estimation for your lasso estimation, then it's perfectly fine. Okay, so post double lasso, we have to do two lassos. The first lasso is related to this equation, epsilon on ZT. The second lasso is related to the second equation over here, target variable on ZT. Epsilon, ZT, we're doing local linear again, so you have to include the first derivative over here. So A1 over here is just the first derivative term. We don't really care about that, but we're including that because we're doing local linear estimation. And then you're going to have the weights, you're going to penalize both the level term and the gradient term, the derivative term. Most of the time, you can set the lambdas over here, the tuning parameters, to be of the same order. They can be proportional to one another. So you can just reduce this to just one lambda. If you have just one lambda, at the end of the day, this is just a simple lasso where you have two sets of regressors. You just combine the regressors into one set. And then for the second regression, you do the same thing over here. You're going to keep the non-zero coefficients. I'm going to call it capital I1. Keep the non-zero coefficients for related to the level term, into I2. And then I'm going to take the union of I1 and I2. And finally, I'm going to do an unpenalized regression of the variable of interest, the target variable on our shock of interest and whatever that was capped in I1 and I2. And then, of course, the gradient terms, the expansions, the local linear expansions, the gradient terms of the respective z's and epsilons. Okay, and then once you have estimated, so basically at the end of the day, this is going to be our impulse response estimate. Again, this is going to be weighted kernel. Now, this is easily done in R. And all of these steps are easily done using the GLM net package in R because at the end of the day, there's no, you don't even have to weight anything. There's no weights over here. It's just regular lambdas. Okay. Okay, I've got some assumptions here, and I just want to point out the main assumption that is different when it comes to the tuning parameter is that we have this this relatively ugly looking rate requirement for the lambda, and that is because we are assuming tau mixing with potential heavy tail type of distributions, and this polynomial. So this term over here is related. If you have not so heavy tails, then this term is going to dominate. If you have heavy tails, then this term is going to be the thing. And then there's an additional term over here, which is related to the local linear approximation. Okay, it's due to the nonparametric approximation, the Taylor expansion of the smooth function over there. So we have, again, some sort of inference result for this, with the estimate of the impulse response data check over here. And then you can also, again, construct the asymptotic variance using sample estimates. You just replace the E with the sample average. And then for the long-run variance, you can use what I suggested over there, which is a byproduct of your estimation. Okay, I'm going to skip the simulation. Basically, the coverage probabilities of the impulse responses, they don't look so good if T is relatively low, but when T is higher, it looks not so bad. I'm in the process of revising the simulation. So, anyway, this paper is under revision, so comments would be greatly appreciated later. Okay, for the empirical application, we are looking at an impact of a severe weather shock on the macroeconomic variables of interest, and we're looking at GDP, industrial production, we're looking at inflation, we're looking at unemployment. This weather shock variable is due to this actuary's climate index, which is some sort of composition of, how frequent days that have temperatures above the 90th percentile relative to a reference period are low temperatures similarly, and also precipitation and things like that. And also they also look at changes in sea level. So this data is publicly available. This was the same shock that was created that was used in this paper over here. This is the model that we're trying to compare with, and the sample period is from 1961 to 2019. Okay, so we are going to replicate this, but we're doing it from the LP approach. We're going to have 12 flags, and we're going to use, if you have 12 flags, by the way, we have, I think, 6 variables in our so-called the VR. So you have at least 6 times 12 flags. So we have at least 72 variables to control for. And when we do local linear estimation, multiply the 72, we have 144 control variables, effectively 144 regresses. So we're going to resort to a post-double Lessor approach. These are the estimated impulse responses. Interestingly, for the 1970, so we are going to situate the impulse response estimation at a 2 time point. We're going to estimate just like what they did. They estimate impulse responses early on in the time sample and then later on in the time sample. We're going to do something similar. We're going to estimate there in 1970 and then later on in 2011. Over here, you can see that the responses from 1970, they are almost completely expected. You have a severe weather shock. It could be a negative supply shock. It forces industrial production to fall in the medium term. Inflation rises, core inflation rises, unemployment rate for some reason declines initially, but then rises later on. Now the interest rate rises probably to do with inflationary pressures. So I would say this is relatively expected. What I would like to mention is that in the original VER paper, the AJ macro paper, they actually didn't really obtain any significant responses for industrial production. Over here, we do see a significant decline. What is interesting actually is in the 2011 result, we have industrial production increasing 2 years out from the severe weather shock, as opposed to declining in the VER paper. Now, this could be attributed to what is known as the build back better effect, in which you have a reconstruction of infrastructure, reconstruction of the capital stock, an inflow of investment, an inflow of disaster aid, and then the local economy could boom. And that is related to, usually those type of effects that people have found in the literature are related to the local economy, and it's a regional effect. But our hypothesis is, given the increasing supply chain management, sophistication of supply chain management, then that local effect, that regional effect, could also be translated nationally, because at the end of the day, we're looking at industrial production. These are measures, national measures. And we do see, relatively, I guess, understandable results for inflation and unemployment rate. But I would like to point out that the magnitude of the variables over here, of the responses over here, it's about 1/5 that of the original magnitude. So maybe we could see this as some sort of resilience of again, sophistication and resilience, improving resilience of supply chain management in the US. And there is some literature, some evidence for that in the literature. You can also plot it over time. We did it for 2 time points previously, but you can plot it. And again, these confidence intervals are constructed from the long-run variance, the method of moments estimator. You can also do this for every single time point, and then you plot the impulse responses over every single time point. We do see that the responses has become more muted over time. In fact, it's like almost monotonic. Unemployment, industrial production, not so monotonic. It might be due to the fact that if it is really due to the build back better effect, then it is related to perhaps disaster aid. Disaster aid is not monotonic. It varies a lot, and could vary for political reasons, for example. And then these things are also going to vary accordingly. Okay, so the conclusion is this, but the main point is the approach that I'm proposing today is very simple. It preserves the simplicity of local projection. So if you're interested, it's just OLS again, weighted least squares basically. So yes, please consider using this for your own empirical exercise. Thank you.
Wonderful. Thank you so much, Kenwin. Wonderful presentation. I'll just stop the recording now, and then we can proceed to the Q&A.
Okay.